The Particle at the End of the Universe: How the Hunt for the Higgs Boson Leads Us to the Edge of a New World by Sean Carroll.
Right.
So our intention for this deep dive is to understand why modern physics required the Higgs field, how thousands of researchers found its associated particle, and really why this discovery completed an essential part of the Standard Model without completing our understanding of nature.
Yeah, that's the big picture.
Exactly. So to guide our journey today, we're building everything around this central question. How did scientists discover the Higgs boson, and what does this particle reveal about mass, matter, and the unfinished structure of our universe?
Well, to give you a roadmap of where we're heading today, we are going to start by stripping away everything you probably picture when you think of matter.
Oh, wow.
Yeah, we have to replace it with a universe made entirely of invisible vibrating fields. And from there, we really need to look at a very real mathematical crisis that physicists faced in the 20th century regarding the whole concept of mass itself.
Right, the mass mystery.
Exactly. So to solve that crisis on paper, scientists proposed this wild theory. But to prove it in reality, we had to journey through, honestly, decades of monumental accelerator engineering.
Which is just a crazy story on its own.
It really is. And that culminates in the construction of the Large Hadron Collider. So we'll explore how the hunt for this elusive particle wasn't about, finding a solid chunk of matter, but a grueling, deeply statistical search for fleeting signals hidden in subatomic debris.
The statistical ghosts, right?
Right. And then we'll relive the historic 2012 announcement that changed physics forever. Finally, we're going to dive into the modern ongoing quest, because finding the Higgs wasn't the end of the story.
I mean, it actually unlocks some pretty strange new properties.
It did. It raised these thrilling and, frankly, somewhat terrifying questions about the actual cosmic structure of our universe.
Okay, so let's start at the beginning. Because, I always pictured the universe at its most fundamental level as a collection of tiny, solid billiard balls.
Yeah, most people do.
Right. You have protons, neutrons, and electrons, and they just sort of stack together like microscopic building blocks. But reading through these sources, it seems like modern physics says that entire visualization is just, well, fundamentally wrong. How did our understanding of matter actually shift?
Well, this shift was revolutionary. Quantum field theory tells us that space is not empty and particles are not solid objects.
Wait, really? Not solid at all?
Not at all. Instead, the universe is filled with dynamic, overlapping oceans of energy called fields.
Oh, okay.
So, like, an electron isn't a tiny sphere. It is just a localized wave, an excitation in the universal electron field.
Oh, interesting.
Yeah. And a photon is just a ripple in the electromagnetic field.
Okay, let's unpack this. Because if I'm hearing you right, the universe is less like a pool table full of solid balls and more like a vast ocean of overlapping fields.
That's a great way to think about it.
But, if particles are just waves in these fields, where does mass even come from without breaking the math? Because our sources talk about this concept called gauge symmetry causing a massive mathematical crisis.
What's fascinating here is that gauge symmetry is basically the fundamental rulebook for how these different fields communicate.
Okay. The rule book.
Right. It's a mathematical principle that keeps the forces of nature balanced and predictable. And in the mid-20th century, physicists developed the electroweak theory.
Which unified a couple of forces, right?
Exactly. It beautifully unified the electromagnetic force and the weak nuclear force, which is the force responsible for radioactive decay.
Okay.
But there was a glaring problem. To keep the equations symmetric and functioning, the rulebook demanded that the carrier particles for the weak force, known as the W and Z bosons, had to be completely massless.
Like the photon. A photon has no mass, so that works perfectly for electromagnetism.
Right, but experiments in the real world show that W and Z bosons are actually incredibly heavy.
Oh, so they are massive.
Very massive. And theorists couldn't just, manually write a mass value into the equations to match reality. Because if they naively forced mass into the math, the gauge symmetry would shatter. The equations would literally break down and start outputting infinity as the answer for basic physical processes.
So it's like trying to change the rules of a language halfway through a sentence. Just turns into complete gibberish.
Exactly.
The math said they had to be massless, but reality proved they were heavy. So how did physicists resolve that without breaking the beautiful math?
Well, they realized mass isn't a hidden substance packed inside a particle. It had to be a property arising from how these fields interact with their environment.
Okay, so it's relational.
Yes. And in 1964, a structural solution was proposed by several researchers working independently.
It wasn't just a lone genius then.
No, not at all. You had Robert Brout and François Englert, Peter Higgs, and the team of Gerald Guralnik, Carl Hagen, and Tom Kibble.
Wow, a lot of minds on this.
Definitely. And together, their work proposed a mechanism called spontaneous electroweak symmetry breaking.
Okay, spontaneous symmetry breaking.
That sounds like a mouthful. Walk me through what that actually looks like.
Think of a perfectly symmetric hill shaped like a Mexican hat or the indented bottom of a wine bottle.
Okay, I can picture that.
If you balance a marble perfectly at the very top, the peak of that central hill, the system is completely symmetrical. Every direction looks exactly the same.
Right.
But that position is incredibly unstable. A tiny nudge, and the marble rolls down into the circular valley at the bottom.
And it has to pick a spot.
Exactly. Once it settles in that valley, the symmetry is hidden or broken because the marble had to pick one specific spot to sit in. The underlying physical shape of the hat is still symmetric, but the actual state the marble settled into is not.
And if we apply that to the universe, that valley represents a new field, the Higgs field, settling into a state where it has a non-zero energy value everywhere. Like even in perfectly empty space, this field is just sort of turned on. That is the crucial insight. Because the Higgs field is settled in that valley, it permeates all of space.
Wow.
And the result is profound. The W and Z bosons acquire their mass by interacting with this pervasive background field, while the photon passes through it completely unaffected, remaining massless.
So it preserved the mathematics while matching reality.
You got it.
And what about the matter particles, like the electron or the quarks that make up our bodies? Do they get their mass the same way?
They do, but through what are called Yukawa interactions.
Yukawa interactions.
Yeah, think of Yukawa interaction as like a specific mathematical handshake between the matter field and the Higgs field.
Okay, a handshake.
Right. Different particles have different coupling strengths, tighter or looser handshakes. An electron has a very weak handshake with the Higgs field, so it's incredibly light.
And heavier particles.
A top quark has a remarkably tight handshake, making it massively heavy.
Wait, pause. This brings up something I really need to clarify.
Sure, go ahead.
If I'm listening to this, I'm probably remembering that famous popular analogy, that the Higgs field is like a giant vat of molasses or a crowded room, and it creates physical drag that slows particles down and gives them mass. Does that still hold up?
Oh, you absolutely have to throw the molasses analogy out.
Really? Completely?
Completely. It is one of the most persistent misconceptions.
Yeah.
The Higgs field does not act like physical friction or drag.
Okay, so what is it then?
It's an energy relationship. Remember Einstein's famous equation E=mc²?
Energy and mass are equivalent.
Right. Because a particle like a W boson or a top quark interacts strongly with the Higgs field, it holds a high amount of potential energy simply by existing in space.
I see.
That energy is its mass. It's a structural energy debt, not, a syrup that slows things down.
That makes so much more sense. It's about energy equivalence, not friction. But, there's another misconception in the sources we need to clear up. The Higgs field doesn't actually generate all the mass in the universe, does it?
It does not. The Higgs field gives elementary particles their individual masses.
Okay.
But if you weigh an entire atom or a human body, most of that mass does not come from the Higgs field.
Wait, really? Where does it come from them?
The bulk of the weight of the protons and neutrons inside your atomic nuclei actually comes from the strong interaction energy.
The Striforce.
Yeah, the binding energy of the gluons that frantically zip around holding the quarks together.
That is wild. The bulk weight of our physical world is mostly just confined kinetic energy.
It's pretty mind-bending.
Definitely. But returning to the 1960s, theory is one thing. Chalkboards don't prove anything. To prove this invisible ocean actually existed, you had to physically ripple the field. And that required building machines unlike anything in human history.
Exactly. To prove a quantum field exists, you have to excite it enough to produce its associated particle, in this case, a skin-zero boson.
Right.
But the 1964 theory didn't predict exactly how heavy this Higgs boson would be. It could have been hiding anywhere on this massive spectrum of energy.
Which means we had to systematically search for it. And we didn't just jump straight to the Large Hadron Collider. There were decades of massive machines that paved the way.
Oh, absolutely. Earlier colliders were essential. The LEP collider at CERN in the 1990s established a strict lower bound for the particle's mass.
So they essentially proved, the Higgs is definitely not lighter than this.
Right. And then the Tevatron at Fermilab in the U.S. searched higher energy ranges, looking at different ways the particle might decay, like into bottom quarks and vector bosons.
Even though they didn't find the Higgs, those negative results were highly productive, right?
Very productive. They fenced in the hiding spots.
Which pushed the scientific community to build the ultimate machine, the LHC at CERN.
Yes, the Large Hadron Collider.
A 27-kilometer underground tunnel spanning the border of Switzerland and France. Here's where it gets really interesting. We're talking about essentially freezing a massive underground ring to temperatures colder than outer space, using liquid helium and superconducting magnets, just to find a single missing piece of our mathematical puzzle.
It is an absolute engineering marvel. It required radio frequency cavities to accelerate the protons and immense distributed computing networks to handle the data.
Just massive scale.
Yeah. But the LHC needed two specific things to find the Higgs: high energy to make the creation of this heavy particle possible, and high luminosity.
Luminosity just means an astronomical rate of collisions, right?
Exactly. Because creating a Higgs boson is incredibly rare, you need to smash billions of protons together every second just to hope a faint signal emerges.
Because the Higgs boson is incredibly unstable, it decays almost instantly. We never actually take a picture of the particle itself. So if the Higgs decays instantly, it's like trying to figure out exactly what kind of piñata was just destroyed by only looking at the specific spray of candy on the floor.
That is a perfect visualization. You can only look at the debris. And to read that debris, thousands of scientists built colossal detectors.
Like ATLS and CMS?
Right. ATLS and CMS are the two main general-purpose detectors at the LHC. They were built with overlapping goals, but entirely different engineering designs.
Which was an intentional choice, right, to prevent false discoveries.
Yes.
Like, if ATLA sees a blip in the data, CMS needs to see it too, using a completely different physical setup. But how do these detectors actually catch the ghost of a particle?
Well, they're built in concentric layers around the collision point. You have inner tracking systems to measure the curved flight paths of charged particles.
Okay.
Then you have calorimeters, which act like dense walls to stop particles and measure their deposited energy.
And the outer layers.
Finally, you have outer systems to track muons, which are heavy relatives of the electron that punch right through the inner layers.
And with billions of collisions a second, how do they even process that?
They use hardware and software triggers to instantly filter out the boring known physics and only say the interesting sprays of candy to the hard drives.
And what did an interesting spray look like for the Higgs?
Well, the primary way the LHC produced the Higgs was through something called gluon fusion via a loop of top quarks. But once born, the Higgs vanishes instantly. So physicists focused heavily on what we call the golden channels.
The golden channels.
Yeah, these were specific decay paths, like the diphoton channel, where the Higgs turns into two high-energy photons, or the 4-lepton channel, decaying into two Z bosons, which then turn into 4 leptons.
Even though those specific decays are rare, they are the cleanest sprays of candy, right? They offer a sharp spike in the data over the chaotic background noise.
Exactly. Excellent mass resolution. Separating the true signal from known background processes that just happen to mimic the Higgs is the entire game.
And this requires rigorous statistics.
Very rigorous. You have to account for the look elsewhere effect.
What's that?
It's the statistical trap where if you look at enough random data points, you'll eventually find a bump just by chance.
Ah, right.
So to claim a discovery in particle physics, you need a significance of 5 standard deviations, or 5 sigma.
Meaning the probability of background noise creating that exact bump by pure chance is less than 1 in 3 million. Which brings us to the summer of 2012. The pressure must have been unbelievable.
It was a monumental effort of human coordination. The teams at ATLAS and CMS were conducting blind analyses.
Meaning they hid the data from themselves?
Essentially, yes. They hid the final data region while they tuned their algorithms to prevent any human bias. When they finally unblinded the data, both collaborations saw the same undeniable bump.
Leading to July 4, 2012.
Right.
But I noticed in the sources, the wording they used at the announcement was incredibly precise. They didn't initially walk out and say, "We found the Higgs boson."
No, scientific discipline requires caution. If we connect this to the bigger picture, identity in physics is a network of properties, not a single snapshot.
Right.
So they announced the observation of a new boson near 125 gigaelectronvolts, a particle, quote, consistent with the Higgs boson. Over the next few years, they had to prove it wasn't an imposter.
With a multi-billion-dollar machine, you have to ask about the public value. It's not just about technological spin-offs, right? It's about fundamental knowledge we literally cannot get any other way. But what did that proof actually look like?
They had to confirm it was a neutral spin-zero particle. They checked its parity, and crucially, they measured its couplings to tau leptons, bottom quarks, and top quarks.
To prove it generates mass for both bosons and fermions.
Exactly. To prove this single field truly does that job.
That really highlights the reality of big science. Answering a 50-year-old question took thousands of researchers, decades of work, and international funding. It's a reminder of how fragile this pursuit is, like the cancellation of the U.S. superconducting supercollider in the 90s.
Yes. Political realities are definitely part of big science.
But okay, they proved it. They found the Higgs at 125 GeV. Does finding it mean the standard model is complete and we can all pack up and go home?
The standard model is complete, but physics is definitely not. The specific mass they found, 125 GeV, sits in this incredibly weird sweet spot. Well, it allowed physicists to study many different decay modes, but it also unlocks some terrifying new cosmic mysteries. Let's start with vacuum metastability.
Oh boy. Vacuum metastability sounds like something from a sci-fi disaster movie.
When theorists take that 125 GeV mass of the Higgs and combine it with the mass of the top quark, the math suggests that the current state of our universe's vacuum, that Mexican hat valley we talked about, might not be absolutely stable.
Uh-oh.
It might be metastable, meaning there could be an even deeper valley, a lower energy state, that the universe could eventually transition into.
Wait, pause. So what does this all mean for us? You're telling me the exact mass of this particle implies the entire universe might just be in a temporary phase. Should we be worried?
Well, you shouldn't panic, because the estimated transition times for the vacuum to decay are vastly longer than the current age of the universe.
Okay, good to know.
But it is profoundly weird that a single number measured inside a collider suddenly connects the microscopic behavior of a subatomic particle to the ultimate cosmic fate of the universe.
Unsettling, but incredible. And the mysteries don't stop there. There's also the hierarchy, or naturalness problem.
Right. The mass of the Higgs is mathematically very sensitive to physics at much higher energy scales, like the Planck scale, where gravity becomes quantum.
Okay.
Without some new undiscovered physics like supersymmetry or extra dimensions to stabilize it, the fact that the Higgs is so light seems incredibly unnatural.
Why is that?
It requires a delicate, almost miraculous cancellation of numbers in the equations. We expected the LHC to find the particles that would explain this naturalness problem, but so far, those expectations haven't materialized.
Which leaves us with a glaring question mark. Speaking of question marks, the Higgs we found doesn't explain dark matter either, does it? The invisible stuff that makes up most of the universe's mass.
It doesn't explain what dark matter is, but it might be our bridge to finding it. The 125 GeV Higgs might act as a Higgs portal.
A portal?
Because the Higgs field interacts with mass, it's possible that unknown particles in a dark sector interact with our visible world only through their connection to the Higgs. Experiments are actively searching for invisible Higgs decays that would prove this portal exists.
So to solve these massive cosmic mysteries, the strategy has to change. The LHC is no longer just a discovery machine looking for a new blip. It has transitioned into a precision scalpel.
We are fully in the precision era. During run 2 of the LHC, the ATLAS and CMS experiments sifted through about 140 inverse femtobarns of 13 TV collision data.
Whoa! Inverse femtobarns. Let's translate that for us non-physicists.
Yeah.
How much data are we actually talking about here?
An inverse femtobarn is a measure of particle collisions. 140 of them translates to roughly 10 million billion proton collisions.
That is just an unfathomable amount of data.
It is. And now in run 3, they are pushing even further, probing rare interactions. One of the biggest current targets is measuring the Higgs self-coupling.
Meaning how the Higgs field interacts with itself.
Exactly. To measure that, you have to observe double Higgs production, where one collision is so energetic it creates 2 Higgs bosons simultaneously.
I imagine that's pretty rare.
Incredibly rare. It's buried in massive background noise. But measuring it is crucial to proving the exact shape of that Mexican hat potential energy hill. We need to know if the hill looks exactly the way the 1964 math predicted, or if it has a slightly different shape that points to new physics.
It seems like we found the final puzzle piece of the standard model, but placing it in the frame just illuminated how much of the broader picture is still missing.
This raises an important question. We still don't know if the Higgs is truly elementary at all energy scales. We don't know why its handshakes with other particles form the exact pattern they do.
Right.
Finding no deviations from the standard model so far is a success, but intellectual honesty requires holding that success together with the glaring incompleteness of our cosmic understanding. The standard model cannot explain quantum gravity. It cannot explain dark matter or matter-antimatter asymmetry.
I love that perspective. Precision isn't an anticlimax after a big discovery. It's a systematic search for the cracks that will lead to the next revolution in physics.
Exactly.
So to synthesize everything we've explored today and return to our central question, the story of the Higgs boson is really methodological. Abstract symmetry led to testable predictions requiring global engineering, stats, and patience.
Yep.
We found the excitation of a universal field, measured it, and opened new doors. We did not finish physics. We gained a new instrument.
If we zoom all the way out and think about what this means on the most fundamental level, it leaves us with a pretty provocative thought.
What's that?
If the Higgs field settling into its non-zero valley is what allows fundamental particles to have mass, and therefore allows atoms and structures to exist, then our very existence is essentially a byproduct of a broken symmetry.
Wow.
We are here because of a mathematical imperfection frozen into the fabric of the early universe.
This has been an independent COSMORA HQ book overview in audio podcast format. It is not an audiobook, complete narration, adaptation, abridgment, reconstruction, authorized production, or substitute for the original work. We highly encourage you to legally access the book, The Particle at the End of the Universe by Sean Carroll.
Thanks for listening.
We'd love to hear your thoughts. Which is more remarkable, that an invisible field helps shape the particles around us, or that humanity built an experiment capable of detecting one fleeting vibration within it?